It is truly my pleasure to represent NSF and speak to you at your Cyber Infrastructure Day. Thank you so much for the opportunity. So let me begin by introducing myself. My name is Rajiv Ramnath. I'm a program officer in the software cluster within NSF's Advanced Cyber Infrastructure Division, which in turn is part of the Computer and Information Sciences and Engineering, or SIS Directorate. So I'll begin by telling you a little bit about NSF and then the programs around cyber infrastructure, followed by where we appear to be headed with respect to CI and what we are seriously thinking about with respect to cyber infrastructure. So to begin with, NSF is all about the science. Everything NSF does is done to support and promote the advancement of science. We are, after all, the National Science Foundation. Our budget, as the slide shows, our budget is about $7.5 billion this year, give or take a cent or two. We've used this money to fund over 11,000 awards to 2,000 institutions in support of now 300,000 researchers, who we call PIs, principal investigators. And we have made these awards after evaluating close to 50,000 proposals. And yes, now that I have been part of NSF, I can testify that our review panels and program officers actually read each one of them and consider every one of them quite carefully. So a question that I'm often asked, and Hadrian asked this question as well, the question that I'm often asked is, what do we mean by cyber infrastructure? So I think the best answer to that was provided by Craig Stewart at Indiana University. He's the Associate Dean for Research Technologies, and he's also now the Executive Director of a new institute there called the Pervasive Technology Institute. And his picture is on the slide as well, just to show that he actually said what he said. Anyway, so cyber infrastructure, in our mind, consists of computing systems, data storage systems, advanced instruments like telescopes and microscopes and hadron colliders and things like that, data repositories, visualization environments, and people, all linked together by software and high-performance networks with the goal of improving research productivity and enabling breakthroughs that are not otherwise possible. So the main takeaway from this is that NSF takes a very broad view of cyber infrastructure to include not just the computing, but the data, the instruments that in many cases provide the data, the networks that transmit everything, both the data as well as the control directives, the software that analyzes and processes the data, as well as providing scientific insights through modeling and simulation, or in stitching the collaborators together, allowing them to collaborate, essentially the people, in all the important ways necessary to advance science. This slide is to reiterate this fact, that it further illustrates the broad view at NSF that we take about CI. We support the data. We think of data as an asset. We support the networking that serves to connect everything together. We support the software that's used to do the stuff. We support the HPC, the high-performance computing, and other computational resources. And we support the expertise. So we support the principal investigators, we support the graduate students, we support the postdocs, we support undergraduate students, we even support K through 12. Okay. So here's where our directorate sits within SIS and within NSF. So SIS, the Computer and Information Science and Engineering, is a directorate within NSF. It has 4 divisions. We are one of those divisions. We are the Division of Advanced Cyber Infrastructure, and we are broken up into 4 clusters that I'll talk about later: data, high-performance computing, networking and cybersecurity, and software. Okay. But the point I want to make is, while we are a division within SIS, cyber infrastructure NSF-wide is coordinated by us. So here are our clusters. We have the software cluster, to which I belong. The idea behind the software cluster is to innovate in research and education and through software, and make these software resources, the shared tools and services, an integral part of the infrastructure. We support the computing resources. So we provide the open science community with HPC assets, ranging from clusters within departments and universities to large-scale instruments, essentially to develop a collaborative and scientific HPC environment. We support the scientific communities in the use of data. So we think of data as an asset. So the data that's generated is certainly used for specific kinds of experiments, but we also expect that the data is then archived and made and tagged and made usable and available to scientists beyond the original creators of that data. We have a cluster on networking and cybersecurity. So we invest in campus network improvements and re-engineering to support a range of activities in computational science. And we support the transition of cybersecurity research to practice. Now, I will say one thing, that cybersecurity, to our mind, is not the fact that it's part of networking is simply simply because the program officer in charge of cybersecurity belongs to the networking cluster. We think of cybersecurity as a cross-cutting goal. So the next slide is once again to reiterate the fact that we coordinate cyber infrastructure NSF-wide. Now, not only do we support other domains, we also engage in research, and our research is different from, for example, what happens in the rest of SciES, because it's extremely use-inspired research and education and engineering. And if you look at the picture on the left, we are in the pastures quadrant of scientific work. In other words, we are use-inspired basic research. We have a small element of pure basic research, and we have some degree of applied research, but we are mostly in this notion of use-inspired basic research. So our domains that we support, the bio domains and the SciES domains and the EHR domains and the mathematical and physical sciences domains and the SBE domains and the geosciences domains, they provide the ecosystem in which our research takes place. And we are driven by their research needs. So this next slide is a summary of our vision and strategy. So the idea is, once again, we support the entire spectrum of NSF-funded communities at the cutting edge of advanced computing technologies, hardware as well as software. Our strategies are to support foundational research, application research, and yes, applied research, but also simply the building, testing, and deploying resources into a collaborative ecosystem. And the education that goes along with it, and then the development of communities. So in a sense, we are the division that helps you make things happen, and we help make things happen as well. The latest articulation of our vision and strategy can be found in what we call our SIF21 Initiative. So our SIF21 Initiative is an NSF-wide funding program to research, develop, and deploy cyber infrastructure in support of new ways of doing research. And we work in basically three primary modalities. Community building, so we assist in putting together that ecosystem of scientists, both end users as well as developers, graduate students, investigators, K through 12 students, and the industry community. We support this community building activity. We certainly support data-intensive science, so the analysis, visualization, integration, identification, the stewardship of data, the workflows around data, the meta-information around data, and all about the management of data. And then, of course, we support the computation aspects of things through computational models, methods, algorithms, and tools. Okay? And just to sort of highlight this, our investments in 2013, we don't have the 2014 numbers yet, we do have the 2013 numbers, our investments reflect this. It is across all the different modalities of SIF21. Now you will notice that a big chunk of our money goes to support high-performance computing. And that's because facilities and hardware and things like that are expensive. But that's not a reflection of the relative importance. We are charged with supporting computing, software, data, education, workforce development, community building, all of those things as driven by and as prioritized by science needs. Now, of course, our computing infrastructure is the most visible aspect of what ACI does. And so let me talk about that a little bit. So we anticipate, firstly, we look to the future, and you will see a little bit of that later when I talk about our future direction. And we anticipate and invest in innovative national scale shared resources and outreach and education that complements what is done in the universities and investments made by other agencies like DOE and so on. We leverage and invest in collaborative fabrics that connect these scientific communities with computational resources and services at all scale: campus scale, regional scale, national scale, international scale. So here are some of our more recent computing infrastructures that were deployed starting in 2013. Most of you would have heard about Blue Waters. Many of you would have heard of Stampede. And many of you would have heard of NCAR at the Wyoming Supercomputing Center. This is Blue Waters. It's a data center at UIUC. The hardware consists of Cray, XE6, XK7 systems. The application projects that are supported by Blue Waters are petascale application projects, earthquake research, earth science, biophysics, astronomy, genetics, molecular biology, things like that. This is Stampede. This is at TAC, where the idea behind this was to enable and enhance petascale computing for science and engineering. Stampede has already completed over 2 million jobs, over 1,200 projects, and engaged 3,400 researchers. Stampede ranks as the 7th most powerful computer in the world, and so far it has completed, I think, now more than 10 quadrillion floating point operations and it is able to do over 10 quadrillion floating point operations per second. So this slide is once again intended to show the diversity of our HPC investments. And I want to make that, diversity and breadth is a point that I want to make a couple of times in this presentation. The fact that we support leadership class computing with Blue Waters, we support geosciences at Yellowstone, we support the open science grid, we have Comet, where the idea is we support long tail science, so many users that use a little bit of compute, but many of them, obviously we support Exceed, and we support Wrangler for data analytics, and so on. Okay, some of these you will notice on the slide set, and by the way, the slide set can be made freely available. Some of them are slated to be retired in 2015, and some of them are slated to be integrated with Exceed in 2015. So, Case Western obviously knows about Exceed. Probably has folks using Exceed. We are seeking to integrate Exceed with ACI Ref, which is a consortium of members that are building community infrastructure with education and so on, using Exceed as a resource. We also have a service called XDMod, that allows you to get data about how the cyber infrastructure is being used for those computer science researchers that can use this data to do research in instrumentation, resource allocation, things like that. So I mentioned SIF21 earlier. I'm going to now transition from the HPC side of things, the compute side of things, to the software side of things. So SIF21 articulated a very broad software vision and strategy, basically saying that NSF will take a leadership role in providing software as enabling infrastructure. So we don't simply think of software as something that is written by a scientist or to enable his or her experimentation. We think of software as being part of the infrastructure to enable science and engineering. So we think of software as an asset. We think that one of our major efforts should be towards reducing the complexity of software for our scientists, so that we advance both the use as well as the development of new software and promote the integration of scientific software across all disciplines. We think that software should not be only in the domain of programmers and software engineers. We think software should be made ubiquitously available to all scientists. Okay? And ACI leads and will coordinate this across NSF. The next aspect of ACI is data. So to illustrate that, I present the One Network for Earth, the Data1 initiative. Data1 has now interacted with almost 20,000 users, has close to 462,000 objects, 150,000 data sets, and metadata records in the number of around 200,000. It's a large and diverse community with several partnering projects, many collaborators. We have been involved with federal and local government agencies, as well as industry such as Microsoft. And Data1 has assisted in tackling such difficult problems such as public preparedness and emergency response. We've advised, Data1 has advised OSCP, the Office of Science and Technology Projects on big data challenges, advised the Federal Reserve Bank, and things like that. Okay. And finally, our big concern, our big focus is people. So we support the development of people, starting from, of course, faculty, researchers, as well as research scientists, and graduate students and postdocs, as well as K through 12. We think that success in the use of cyber infrastructure to advance science depends upon a vibrant and educated workforce. And we support learning and workforce development initiatives targeted at this broad swath of expertise. Okay. And then I want to close this section by saying that we believe in this expertise because computational science has finally taken the Nobel stage. We have had 3 Nobel laureates in chemistry whose Nobel Prizes we can point to the use of the molecular dynamics methods that now run on NSF-supported HPC systems. So we want to develop more folks like that at all levels. Hopefully more of them will end up winning Nobel Prize. Okay. So the next part of my talk is talking about some future ideas behind cyber infrastructures. So, cyber infrastructures have traditionally been the HPC, the networking around them, the software that allows folks to access these resources over the networks. But now we think that the definition of cyber infrastructures have become much more broad. So we think that cyber infrastructures now include mobile devices, social networks, intelligent sensors, as well as advanced computing instruments at all scales. And we believe that these have created a complex, data-rich environment for now new scientific and engineering advances. And we want to be able to support all of this. We think also that all these resources that are being made available has happened side by side with people becoming smarter about developing more complex models that can result in new insights. So for example, now that the data is now available and our scientists and so on are able to do modeling at many more, at multiple scales, and now this modeling is supported by the power of the infrastructures, that transformative results are possible, and we would like to support that. So climate modeling, wind tunnel testing, modeling and simulation without physical prototyping, scientific discovery in astronomy, all of these can be supported at immense scales, well beyond what could be supported when we started on this path, many years ago. Okay? And across many disciplines: molecular dynamics, cosmology and astronomy, plasma physics, quantum physics, earthquake research, and gene sequence analysis. And we think that this research will take place now in new research contexts. That is, research will not be best advanced by single PI research, but rather through interdisciplinary, team-oriented, global, data-driven workflows that are increasingly needing and integrated with technology. Now, technology comes with power, but also with challenges. Everything is instrumented, but now we need a workforce that can use this. We have ubiquitous connectivity, but now we need folks who can take advantage of this connectivity, things like this. The funding landscape has also shifted, and I'll talk about that a little bit as well. We have to find more sustainable ways of supporting this research. And we are also faced with changing demographics. So we need to increase the diversity in our scientist pool, simply because we have a greater need for more computational and data scientists, if for nothing else. So one example of where all these themes are available are made visible is in the Large Synoptic Survey Telescope, or LSST. So we have the base facility, we have the image storage, we have the data communications network that is international, and we have the NCAC Archive Center in Illinois that is doing all the processing. So we have all these diverse, distributed, international sites. We have all the people working at those sites. We have all those people connected together through international scale cyber infrastructure. Another aspect that's driving us is that we are being asked to expand public access to the results of federally funded research. So we have a NSF-wide public access plan in the works that consists of the published results of the work, papers and things like that, but also the data that's generated as well as the software that's generated. We have to make that archivable, linked to the work that is done, linked to the funds that support it, made available publicly, things like that. And this slide is there to illustrate the fact that this public access requirement has extended to data. So we need to make the data open and machine readable for all research that is funded by the federal government. We want to make available enterprise data, but of course limited by relevant law. We want to make, so right now investigator data sets resulting from NSF funding are not covered. Of course we need a data management plan, but that is likely to be in the works as well. The second thing that is coming up the pike is the BRAIN initiative. So this BRAIN initiative was announced in April 2013. NSF contributed $20 million to a White House initiative to better understand the brain. NSF-supported research in this area will span biology, mathematics, physical sciences, engineering. It will drive computer science work, and it will provide an orthogonal angle to social and behavioral science research. The thematic areas in the BRAIN initiative are listed on this slide. Multi-scale integration of the activity and structure of the brain, tools to image, sense, and record brain function, and develop theories and systems to collect, visualize, analyze, model, and store and distribute brain data. The quantitative theory and modeling of brain function, using what we know about the brain to create novel computational paradigms, for example, and then once again, since workforce is so important to us, workforce development around the brain. Now let me transition to one other thing. So traditionally, scientific research has been done by systems that we traditionally call HPC. But if you look at what has happened in industry work, Google and Amazon and Netflix and Facebook are supported by what we call the cloud. Okay? So the left top half of the slide is what we do as science, and the bottom right part of it is what we call the cloud. Okay? And the point I want to make is, that the architectures of these two systems have diverged. Okay? Now, at one point, science was supported by supercomputing, craze, and special purpose supercomputing systems like that. We realized, thanks to work done by folks like Dan Reed, that commodity hardware is best for supporting science. That as the scale of science evolved and increased, we needed to support parallel computing, and the best way to support that kind of parallel computing was through commodity hardware. But over time, the architecture being used for science has diverged, has evolved independently from the architecture that supports the cloud. And this slide is it shows how these have diverged. So on the cloud, at the application level, we have applications being written in many languages, typically now in things like R and Mahout. We have middleware that consists of Hive, Pig, Scoop, and Plume on top of MapReduce. MapReduce is everywhere. We have big table file stores. We have the Hadoop file system that runs on VMs and containers and cloud services on essentially commodity networking. Whereas on the right side, we have applications and community codes written in Fortran and C++ and Python using IDs specific to this community. We have domain-specific libraries, domain science-specific libraries, molecular simulation libraries, linear algebra libraries, things like that, that run on things like MPI and OpenMP, that use batch scheduling as the primary paradigm, as opposed to any kind of real-time computations. We still run on Linux, but the use of VMs and containers and cloud services is rare. And we run on different kinds of hardware from essentially what the cloud runs on. And the question to ask is, as the research merge, as the science needs merge across and start using, for example, data that's sitting in the cloud to be analyzed by the computing that we have in our supercomputing resources, should there be a next generation architecture that in a sense unifies these two? Now this slide is courtesy Dan Reed, who is VP of Research at University of Iowa. His talk actually is on the web, and I would encourage all of you to go to take a look at this talk. His talk that talks about the need for this next generation. Okay. So given all of this, the question to be posed is, how should cyber infrastructures evolve? So we think we should create cooperating national and global cyber infrastructure. It shouldn't matter where the physical facilities sit. Everybody should be allowed to should be able to use it. We need to develop models of sustainability, specifically for software and data, that allows efforts to be sustainable beyond the funding models that exist today, NSF funding models and other federal funding models and state funding models. We need to be able to provide access, ubiquitous, capable, secure, and easy access for many, many more researchers, essentially tackle the long tail of the research community. And once again, we need to seriously take on the learning and workforce development challenges. A big push that you will see from NSF, the big message that you will see from our division and from individual program officers is that when research is proposed, when new facilities are built, that investigators and organizations give serious thought to sustainability. That we want to create cyber infrastructures that A, will sustain long-lived ecosystems, and secondly, we expect these long-lived ecosystems to sustain the cyber infrastructure. So one thing I can do is stop for 10 seconds and see if there are any questions. If I don't hear any questions for 10 seconds, then I will go on to the next portion of the talk, which is our funding opportunities, which is a funding opportunities section. So I'm sure all of you are interested in what kind of funding opportunities we have to offer. So these are once again in the categories of computing and networking resources, data and software, and then cross-cutting themes like cybersecurity. So we'll start with the campus cyber infrastructure initiatives. So the main one is this one that is now called CCDNA, Campus Cyber Infrastructure Data Networking and Innovation Program. And originally it had other names, CCIIE, things like that. This year we've resolved to call it CCDNA. Okay. The emphasis this year will be the integration of data and the data infrastructure activities with the network infrastructure activities. Okay? Certainly, we will maintain investment in campus networking and innovation, but we are now seeking to integrate the data aspect of things with the network aspect of things in the 2015 solicitation. And one concrete change we have made is that we had a separate program called the Data Infrastructure Building Blocks Program, or the DIBS program. We have merged that in, and we have commingled, brought in the funds into one program, the CCDNI program. The second set of programs is around cyber infrastructure security. So there are two programs here. It's the Secure and Trustworthy Cyberspace Program, or the SATC program. And our division specifically provides funding for the transition to practice, or TTP, part of the program. So the main size and other divisions and domains might fund the research. We are specifically funding the TTP aspect. So this program seeks to address cybersecurity in a holistic manner, from a trustworthy computing systems perspective, as well as a social behavioral perspective, as well as a economic sciences perspective, and also from the ground up, from the materials, from the chips, from the subsystems perspective. The second program here is the Cyber Innovation for Cyber Infrastructure Program, or the CICI program. The idea here is to address unique cybersecurity challenges of these complex, distributed, interconnected cyber infrastructures and their ecosystems. So think about these sensors that are global, connected by these networks that are global, that are feeding computing resources that are global, that are connecting scientists that are global. These cyber infrastructures are potentially vulnerable and potentially targets of attacks because these are being used to do science that can inform policy with, for example, climate change policy with wide-ranging impact. So we believe these systems should be protected, and this is what the CI program is about. We also realize that making these systems available to cybersecurity researchers allows folks to do research on an available cyber infrastructure, security research on an available cyber infrastructure. So that is the second angle of this program as well. Let me move on to our investment in data. So we are supporting foundational research in how to deal with data. We are supporting the data management process, the curating, aggregating, analyzing, archiving, and accessing process through software and infrastructure. We are looking at community building, and we're looking at workforce development, and we are contributing to policy. So we see data-focused cyber infrastructure as a view towards the future. So we want to catalyze interdisciplinary science and engineering and research and education through data being maintained as an asset. So data, once again, is not something generated by during an experiment and then thrown away. Data becomes a first-class asset to be curated and managed and made available. We want to make these resources available in a shared way, and we want to advance the capabilities for being able to capture, manage, and analyze this data. So software and infrastructure that, for example, deals with the provenance of data or the reproducibility of experiments on data. That's the kind of things that NSF supports. We want to ensure that data-focused cyber infrastructure remains advanced, is in some sense its own leadership class of capabilities. We want to ensure that the workforce we create can consists of data scientists essentially that can use this data, and we want to be able to contribute to policies for this data, as well as all the other assets we create, all digital outputs we create. We want to contribute to advances in policies fed back to OSTP and the White House and so on. And obviously, we need your help in doing this. So last year, we had the DIBS program. I'm just putting this up as a means of showing the history. This DIBS program, as I said earlier, has been folded into CCDNA. So now let me move on to software, which is my specialty. And we're basically supporting three major initiatives, with the prime initiative that is housed in ACI being the SI2 program. So I will talk about SI2 in some depth, but before that, I will briefly mention the other two programs, CDSNE and XPS. So the idea behind XPS was to support foundational research in parallel computing. So most of the research projects are in size, but we co-fund those projects that are use inspired, that potentially could translate into results that could be used within cyber infrastructure. We support the CDSNE program, which is essentially scientists seeking to create software tools for their own use. And we attempt to build upon these two through the SI2 program. And the SI2 program is composed of three elements. The first is the SSE, or the software elements program, where the idea is a scientist or a PI has created some software component that has proved to be useful to him or her. They now want to make this available to their community, and SSE projects allow them to make that component product quality, engage with their user base, and make a component, a scientific software component, available to their user base. The SSI program builds upon the SSE program by saying that when scientists work, a chunk of a major part of their scientific experimentation workflow is supported by software. And several software elements are used within that scientific workflow. And SSI proposals are about integrating these different elements into a larger framework that essentially is a whole product that is provided to a community. So think of workflow tools like Pegasus, integrated with software elements that do different kinds of analysis, integrated with containers that enable reproducibility, integrated with elements that allow data management. Something like that would be a framework, and that would be supported by an SSI proposal. And actually, we are going through our first round of decision making with respect to funding all the SSIs. So our first round of SSI proposals are in the process of being awarded. And then finally, we have the Software Institute's proposal, where a community decides that their needs are best met by an ecosystem of software and expertise and services housed within an institute, which could be at a single location or at multiple locations. And NSF will fund an institute for up to 5 years with a pretty large chunk of resources, of money, to basically support this community through software. So maintenance of software, ongoing development of software, training of the community, educational systems, educational offerings, services, all of those will be supported by software institutes. Now we see the software elements, the software frameworks, or SSI program, and then the Software Institutes program as sort of a progression. It doesn't have to be that way, but we see that as a progression. Wanted to give you one very good example of an SSE project. This is a project by Beth Flail at Indiana University and Craig Mattox at University of Miami. This project developed more than one software tool to run a large number of simulation tasks in a cloud computing environment. The cloud environment provided the opportunity to lease computing resources on demand, as opposed to being restricted to just pure HPC resources. And the idea and the scientific problem that was being addressed by this project was to be able to predict surface water levels, resulting, storm surges and things like that, from tropical cyclones, hurricanes, things like that. Okay. These analyses were done using packages that enabled ensemble computing. Scientists were able to predict storm surges with a high precision. The idea of, with potential users being the National Hurricane Center, FEMA, U.S. Army, folks like those. Now, I had said earlier that the ACI program supports infrastructures NSF-wide, and I wanted to also talk about a program that I became part of, whose first round is currently in the process of proposals have come in, and we're in the process of paneling and evaluating these proposals. This is the CRISP program, or the Critical Resilient Interdependent Infrastructure Systems and Processes programs. So the idea was to look at critical infrastructures, dams, roads, bridges, waterways, look at the interdependence of these infrastructures and see how these interdependent infrastructures could be made more resilient through the research in this program. So the idea was to create multidisciplinary, because multiple types of scientists had to be engaged at multiple levels, starting at the individual operational SCADA level, going all the way up to the large system level, to the the connection with other infrastructures level. So multi-level models for analysis, prediction, real-time control, and adaptation. Try to understand that and see how policy changes might affect the resilience and operation of these interdependent infrastructures. And you will notice that we went quite broad with respect to the computing aspects of this. So we will even support the validation and verification and software integration and software engineering processes needed to interconnect these infrastructures. And we required that in order to bid for this program, that at least one engineer, at least one computer information computational scientist, and at least one social, economic, or behavioral scientist had to be part of the PI team. And we proposed capability building and data collection projects, type 1 projects, as well as assuming that an ecosystem exists and data can be collected, type 2 projects that allows you to do empirical analysis studies, basically where the rubber meets the road, what was all about type 2 projects. So the last bit of our initiative is about learning and workforce development. So here we want to emphasize that domain scientists as well as cyber scientists will be supported to essentially become computational scientists and data scientists, as well as architects and designers, software engineers, things like that, in support of all this infrastructure. Okay? And here are different programs that support learning and workforce development: careers, REU sites, STEM-C partnerships, the cyber learning program, and then the IGERT program. This slide is an example of a career. Maps for Cosmological Discovery, John Kovach at Harvard University. The different projects aims supported by SAIS and ACI are listed here. Here is an example of an RU site. Dr. Bird at Clemson basically got both undergraduate students as well as K-12 students actually to have deep experiences in visualization, computer science, genetics, and so on. So this is my final takeaway. So my final takeaway really is that NSF and ACI is looking to establish and maintain cyber infrastructure ecosystems. We think that build it and they will come approaches are once in a lifetime opportunities, like the internet. What we really want to do is take the ecosystems we have, systematically integrate them, identify what the drivers will be for this, identify the stakeholders, provide support to get the necessary buy-in, engage evangelists, find complementary investments to make all of this happen, and essentially build resilient foundations for these ecosystems through committed partners, aligning metrics and incentive structures, and so on. So this is what we would like to make happen. And we will make ourselves available for dialogue around with anybody interested in doing this. We'll make that available. We'll make ourselves available to figure out how to do this. Okay. So with that, my next to last slide, which is that I had asked Hadrian at the beginning, what do you want me to talk about? Here are some of the questions he asked. So did I have any, are there any questions that my talk did not answer? I'm leaving, I will open up the floor for questions. And of course, thank you. We support proposals ranging from SSEs, which are smaller proposals, to SSIs, which are intermediate-sized proposals, to software institutes, which are $5 million, multi-million-dollar proposals that are going to be handled through cooperative agreements. So once again, the underlying theme here is innovation, community building, ecosystem building, and sustainability. So so we have to start somewhere, and that's what the SSE program is about. We have to build whole products that can support a community in a holistic manner, and that's what the software frameworks program is about. And then we need to create something big that can sustain this for multiple years and potentially build a platform for a foundation for sustainability. And so that's the Software Institutes program. So all of those. And one thing I wanted to let you all folks know is that if you have a proposal idea, one of the things that we are always open to is for you to call us and ask things like, which program is this appropriate for? And to some extent, you can even ask us what we think of this idea. Although remember that we don't decide what is awarded and what is not. Okay, so we are happy to provide direction and advice through email, telephone calls, etc. And if you visit DC, set up appointments with us to talk with us directly.
Now that you're including software engineers and data analysts within the principal infrastructure, what type of benefits have you seen already, and what do you look like to see in the future? So
the question is, now that we're including software engineering, how has that impacted what we support? So we are asking our remember, all the work is done by our our awardees. NSF doesn't really do much work. So what we serve to do is to guide and influence. And what we are doing is we are trying to guide and influence our investigator teams to incorporate a thoughtful, well-defined software engineering process within their activities. In fact, we are asking them in the proposals to define what that software engineering process is going to be. How are you going to work? Are you going to get end-user engagement? Even down to as they become more sophisticated, as folks become more sophisticated in software engineering, to things like, are you going to follow agile practices? What agile practices are you going to use? What tools are you going to use to do your software development, collaboration, and so on, things like that. So we are asking for more engineering things in addition to the science things, if that makes sense.
Thank you.
Okay, let's give thanks again to Dr. Ramnath.